All right, hello everyone, welcome back. Oh, where's my microphone? Do you guys hear me? All right, I'll put the microphone on, but I can continue talking. So everybody had to submit their quiz by 3 o'clock. It's closed now. I usually post the solution after the deadline, and it will be on Carmen. Now, there are 2 ways of checking. One, it will appear under the assignment, just shift it. And 2, it would be in CP homework exam solutions. So once I have them, I'll post them and then you can find those there. So again, CP1 and CP2, which is today during the class, just to give you an idea what kind of quizzes or assignment you will see in the class. So I will consider if this was like your first time, first quiz, I lost 2 points because I didn't read invariant and variant very properly. It's okay. It's not the end of the world. That's the goal, for you to learn and pay attention. So look at CPs as learning experience, okay? And then in your homework, you have to use those knowledge to solve problems. And exams, show me you've done them yourself and you learned them. And then get an A. How can I do this? All right. So the other type of class participation that you will see would be during the class, you work on a problem like today, and you'll submit it on Carmen. I only accept PDF. So if you take a picture and submit a picture, I won't accept it. The reason is when we are grading it, the aspect ratio changes so much. So sometimes it's just really huge. We have to download, say we can just grade quickly. So if everybody, if you have iPad, you can just save that page and submit. If you don't, you're writing on a piece of paper, take a picture with your phone, install CamScan or anything that convert to PDF and submit that. And since you're submitting under your name, you really don't have to rename it, but if you did with your last name or first name or initial, it would be nice. Okay, sure. We try to grade your class participation really quickly, so you can kind of see how much grade you accumulate, especially toward the end of the semester. It becomes important for you to know. All right. Any question on that? No? Great. So I'm gonna stop sharing this one and then share the slides. Also, if you feel sick, let me know and don't come to the classroom, because if you feel sick, you come to the classroom, then you test positive, everybody has to go test and I have to cancel the class or move it online, not cancel. It's not very convenient. So I'll try to work with you to get you at least until tested and see what's the action item. So today I picked open versus closed loop for our lecture. So the quiz had 6 questions. So if you solve the quiz the same day or the day after, you had 6 questions, and then if you did afterward, it was 5. I deleted the first question, which was about closed loop system. The writing was a little bit misleading, so you could have gotten either way, true or false, or true or false question. So I deleted that. I'm going to talk about it. That's why I chose this. So I'm going to show you what really closed and open loop means and why we're doing it. If you had robotic, you already answered it right, because I checked a few. But if you haven't, from what I said last class, you could have gotten wrong. All right. So everyone's grade is from 7 for the class participation 1 instead of 8. Originally it was 8. All right, so quick review of linearity that we went through. We checked last class. A function fx has the superposition property. If you can say fx1 plus x2 is fx1 plus fx2, which is y1 plus y2. So you can superposition. So input signal on a system has this output, has an output. If you add those inputs, create a new signal. If the system is linear LTI, the output should be also the superposition of all the previous outputs. That's property 1. Property 2, a function has homogeneity property. If you scale it by alpha, scale up or scale down, if you scale your input signal, your output signal will be scaled the same way, right? Now, if a system has both of these properties, it's linear. Now, LTI is linear and time invariant, meaning that by changing time, the only thing that happens to the response of the system is that it shifts. Nothing else will be added to the system, like the example that we saw, right? So think of a sine wave. If you shift it through time, the whole thing will just shift, but the function will remain the same, sine, cosine. So those are really good examples to think about when you're talking about shifting in time. Now, I brought 3 examples. I think 2 of them, well, I think I talked about 2 of them. So here, if y is sine of theta, now here, our function, our output is y, our input is theta. What happened to time? Where is time? We live in time. So either theta is function of time, right? Or, well, we are not in frequency, we are in time domain, so sine of theta. So we just didn't say theta is function of time because you will see t is the independent variable. We live in, if we are talking in time domain and we know we are in time domain, we can eliminate that and not show it. It's just faster to write. So this is basically y is sine of theta t, right? So for laziness purposes, since we are in time domain, we can just not write it. Now, is this LTI or not? We talked about it last class. It's not. So look at this here. Let's say if tau was, if we scale it to tau, right? To theta, sorry. Then my y prime, my new output is going to be sine of 2 theta, which is 2 sine of theta cosine of theta. So this part is 2y, but this is a new part that I added to my function, right? So this is not LTI because it's not linear, right? So once you can find one reason, one of the condition that doesn't hold, you just stop, it's not LTI. So now what kind of problem between the linear and time invariant is just not linear, right? So it's a non-linear system. Could be time variant, time invariant. Here is actually time invariant, doesn't change with time. Now, we talked about this. So if X was, so this is a review, just helping you to remember what we talked about. Let's say if X was 2X or AX, let me just say AX. AX, my new Y prime is 2 squared X squared of T, right? I'm just not writing T here. So it's 4X squared. While it should, if it was LTI, it should have been 2X squared, right? It should have been just scaled by 2. Since it's not equal, this is also not LTI because it's not linear, right? Now, how about this one? This was in your quiz, and I think a couple of you got this one wrong because the first part, this actually is linear. But because we have a constant added to it, now if I say, hey, X is going to be AX, right? So I'm going to drop T, is easier to write. Let's see what is my new Y prime. So it's M A X plus B. Agreed? Now, if it was LTI, the output should have been scaled by A. AY would be AMX plus AB. So you see these 2 terms are not similar. So usually when you have a constant added to a linear system, you're making it nonlinear. This is the equation of a line, right? So linearity and nonlinearity doesn't have to do anything with being a line or a curve. Does it hold the 2 conditions we talked about? Okay, so this is, so not that this was a tricky question, this was a question for you to see and you would never forget, right? So any question? No, we good? All right, so also someone asked about if it wasn't linear, or if it wasn't time invariant, what will happen? So that will happen sometimes, especially when you have a differential equation. So those are also like they are basically the dynamic, the equation of motion, right? All of them are partial differential equations. What about them? Are they linear or nonlinear? Now, a differential equation has a dependent variable and independent. The independent variable, if you are in time domain, is t, because no matter what, time changes as we live, and we cannot manipulate it. So we can't do anything to time, right? Unless we have superpower with Doctor Who, then we can, but you're not. Our independent variable is the variable that is function of time. Let's say that x, y, z, you see x of t, y of t, z of t, right? So that's your dependent variable. Now, in your differential equation, you have different time derivative of your dependent variable, x dot, x double dot, x triple dot, all of those, right? So a differential equation that appears as such, that has the time derivative of your dependent variable, but the coefficient of those are constant number, they are linear, all right? Sorry, they are time invariant and also linear because it will hold if you try, because there's no variable in the constant. So when I say constant, what do I mean? So here 3 is the coefficient of my variable, right? And it's a constant number. What's the coefficient of x double dot of t in that equation? 1. 1 is also a constant number, right? So this is a linear and time invariant because time also doesn't appear there as well. Now, what about this guy? U of t. This is function of time. What is U of t is another function. What is that? It's not our dependent variable. So in differential equation, we usually organize the equation such that on the right-hand side, we have the input of our system, right? So you have a dynamic system, let's say car, you model your car, you get an equation. If there is no force applied on that object, on that car, the right-hand side of your equation is 0. Once you start applying forces or torques, then something will appear on the right-hand side. So the input to the system does not determine the linearity or time invariancy of our system. So if I give you something like that, you will say, okay, my equation, my system is actually x double dot of t plus 3x of t, right? All of them that has the dependent variable equal to 0, a constant number, whatever. Now, we will discuss if this system is time variant linear or not, because we care about our system, right? Now, let's take a look if a coefficient of one of those variables was a function of time. For example, here, sine of t. Sine of t is function of time, right? But sine of t is not the dependent variable. It's just a function that changes with time. So the linearity part is fine, right? It's still, here is 1. Here, if you think, is sine of t times 1 times x of t. This case, we have time varying system, but still linear. That's where the time varying happens. So again, we do not care about our input. How do I know that's the input? Well, is that u of t. If it was e to the power of 3t, how about that? Is this part of our system or this could be an input? Let me write the example like this. If I had x double dot of t plus sine of t x t minus e to the power of 3t equal to 0, which you can bring it on this side, right? Rearrange it. I didn't even arrange it for you. Now, e to the power of 3t, is it part of my system or is it the input? Why? It's the input. Why? How do we know? It is function of time t. You're correct, but you need to look at it. I think you know what is the solution. It's not the function of the dependent variable, x of t, right? So it's not the function of x of t, right? So it doesn't have any of the system dependent variable. So it could be our input. So we can omit, not look at it, and say, this can go on the other side, and this is that u that we say we can omit and not look at. When we are deciding if our system is linear or nonlinear, when we analyze, we have to consider the input, right? And then now that's about time varying part of it. Now, what if the coefficient was a function of the system dependent variable? For example, here, x double dot plus sine of x, x of t is u of t. So this x is sine of x of t, right? Again, for laziness purposes, the t was dropped. So now this becomes nonlinear because this is the dependent variable and we have a coefficient because this is our dependent variable x of t. So x double dot, so we are in differential equation. X double dot, x dot is missing, the coefficient is 0, fine. X, right? Now the coefficient of x is function of the dependent variable. Now this becomes nonlinear. Good. So it's the different cases. Now, the reason I brought it here is that we are not going to focus so much on linear, nonlinear. We are going to actually find a system and analyze the system. But it's good to be able to recognize if the system is LTI. Why do we want an LTI system? Do you remember we said we are going to use either two representation, transfer function, or state space representation? For transfer function, we said we need an LTI system. And we talked about impulse function. If we have LTI system, we find the impulse response of our system, then we can build any signal. So we want to make sure our system is LTI, or for simplicity, we start with LTI system. Once we learn them, there are methods of solving nonlinear systems. There are different methods. I will show you one today at the end of the lecture, but there are different ways of solving them. So we want to make sure we are able to recognize the system's linearity and time variancy because we like to only deal with LTI. All right. So this will appear in your homework 1 probably, just to make sure that you understand the difference. But then we will be fine. I'm not gonna concentrate too much on it. All right. Any questions so far on the review part? All right. So open loop system. We did take a look at open loop system last class. So the input acts on the system over time, produces output. That's basically how we define the system. The system input output, right? The specification of the system is that the input never sees the output, doesn't know what happens, right? So you apply, you still have input. You just don't check your output versus input. It means that you don't care what the output of your system is, whatever. You can trust it, or it's good enough for you that you don't need to do anything else. Think about the dishwasher in your house. I mean, they are very smart these days. I don't know how smart they are, but mine has a bunch of buttons. So the input, I press start, like literally, it's planned. 1 hour, I get dishes that are supposed to be clean. Sometimes all of them are clean. Sometimes there are a couple of, I don't know, piece of food that resisted to be cleaned out still on the dishes, right? So this is an open loop system because I really don't care. Worst case scenario, I'm going to wash it again. It doesn't worth my time or the money to pay extra $1,000 to buy something that's super smart. So I get them clean in the first round because my application is not important. Now, if I was working in a hospital, If it was related to someone's health, yes, then I had to make sure that everything is clean on the first round because I'm using. So really depending on application, you choose your system, right? Again, it is really important what kind of system you're using. So now if that's the case, open loop system, we have an input here in this scenario. Our input is our runtime, right? Which is like 60 minutes, let's say. Then inside that dishwasher is a timer. When you put different buttons, the best, actually better than dishwasher is the washing machine because you actually can see the time. So when you put the load, sometimes at 58 minutes, 30 minutes, I think it has a weight, like it weights the clothes and says, okay, if it was between these two weight, wash for 35 minutes. You see 35, you press, so there is a timer inside that goes off at 35 minutes. Then you have something that does the work for you. So now dishwasher is the water jet. And washing machine is probably the thing that spins, water jet, the thing that releases the, I don't know, the detergent if you're using the top drawer. I just put the pot in there. So that's your actuation part. Things happen. Then what you put inside, like the dishes, the clothes, those are the process. The actuation happens to them, right? They will be the product of us. The clothes will be clean, the dishes will be clean. And then your output is their cleanness that they're being done, right? So here, if I say this is my controller, then these two, I can call them plant. Actually, I'm gonna call them separately for now. I'm gonna call this actuator and call them process. And this is my output. So dish cleanness is the output. You see that the input and output really don't relate to each other. Time versus cleanness, right? Or when you put a bread in a toaster, press a button, timer, versus how brown it gets or how toasted it gets. If you want more toasted, you do it again, you change the dial, so it means just more time, right? So all three of these, you're controlling the system still, but you're not manipulating your controller. You say that, okay, I'm gonna run you for this many minutes and I'll see what happens, right? So when we have open loop system, it doesn't mean we don't have a controller. It just means we are not looking at our output and manipulate the process again. And when you are drawing the block diagram, which we will do it in the next slide, or this is kind of like diagram, but it just has all the pictures. You have to identify all these different components. Input, if there's a controller, which part is your actuator, which one is your process, and where's the output? Sometimes you have more component in between. We usually package these as our plant. There could be more things inside of it. So we can say we have input, a controller, plant, that could have actuators, the process, a couple of other sensors, maybe, I don't know, to depend on system. And there's an output. So make sure that you always identify these. Now, this is more in block diagram sense. So you'll see that your input is usually for open loop system, a commanded variable. So in the last example, what was our commanded variable? Timer, yes. Time was our commanded variable. Run for 3 minutes, run time, right? So we have commanded variable, which is our input. Then we have a controller. Now, after the controller, we have a signal that is good for actuation, because after control, we have our actuator, right? So it's a control signal. The controller, depending on what the actuator is, will output different kind of signals. Sometimes our actuator uses voltage. Sometimes uses PWM signals. Really, I don't know what kind of actuator you're using. If it's a DC motor, then we can control with voltage probably, right? So this signal right here really depends on what the actuator is. But if you look at it, these two are not the same. what comes out of your controller. So if you said, let's say I'm driving my car, I'm gonna go 25 miles per hour, grandpa, whatever. So that's your commanded variable, go 25. And then you do things, the control say, okay, to get there, I have to like add this much gas or push the throttle this much. And then increase, something will happen, and then increase the voltage to this other system this much. Now that can spin faster, right? There's a decent motor or something in your system. So these two are not the same. Your desired speed and what actually does the work after the controller, they are not the same. So I think that was the problem with question 1 of the quiz. It was not very clear. Now, commanded variable, your controller, you have your actuating signal, then you have your actuator, right? For different systems could be different things. Should be able to recognize what's the actuator in your system. Then you have your manipulated variable, which applies to your process. And then you have your control variable. So any system you think of, you should be able to put it in this format, in this block diagram. All right, we're going to practice this. That actually will be your class participation. Now, think about sprinkle system. Everybody have seen one, right? So what is the input to a sprinkle system, a normal sprinkle system you see on someone's lawn? Time. Just, right, Jesse? Runtime. So it will be timer. Right, so this is your command, then there's the timer. Then what's next? What's the actuator? So we need an actuator now, right? Timer is the controller. Oh. So runtime is your input. Timer thing is the controller because it can go off and cut this circuit, probably that's how it stops. Then what's after timer? Let's say we are still within the time. The sprinkle thing, right? Yeah. The whole thing. It's just very simple. It opens and it spins, something spins in there. So I'm gonna say sprinkle. So this is a module that has the whole thing. I'm gonna just call that. This is my actuator, right? And then what's next? Do you remember? What do you need after your actuator? The process. What's your process? Grass, plant. I want to make a joke, literally plant, but this is a plant. This is not a crown. Grass. This is your process. And then what's next? This output, right? The wetness of the grass or the soil moistness, whatever you want to call it. I'm gonna say watered grass. Let's just be it. Water grass. So this is my output, my input. Controller, and these two are plant. Okay, now there goes my joke that nobody laughs at. Right? Very simple. We still have a controller, right? And we have all the components. So let's look at a more familiar example, maybe that you've seen before. Think about any object that rotates, like a rotating disc, flywheel, or the wheel of your car. There's always like a DC motor or something connected to it that rotates it, right? And then you need a controller so you know how much voltage you have to feed to that motor. Now, if we say that, hey, rotating this, we need a DC motor to move it, we need an amplifier to be able to amplify to get the voltage where we want to be. I want this disc to rotate 3 miles per hour. Or 10 miles per hour, right? How do I tell my amplifier 10 miles per hour? We can't say that, right? So amplifier is our controller. So the variable that we feed into our controller is very different with the variable that comes out of controller and applies to the actuator. Because for actuator is the RPM, right? It goes this much or so. But your controller, 10 miles per hour doesn't make sense, or 10 RPM doesn't make sense. So you'll see that a lot of time we have battery that we can control voltage, and every voltage will mean something for our motor, right? So usually control with PWM. So think about it, that your control input is not always the same as what actually goes to your actuator. That's why your controller is there. So it converts the signal to something that's usable. So here in this example, you will have a battery that has a speed setting. So if you click 1, 2, 3, 4, 5, it translates to this much voltage that will go to amplifier, that will go up to your motor, that will create that much of RPM that you want. Now, draw the block diagram of this. You don't have to submit this one. Just I want you to get used to drawing. Draw the block diagram and identify all the components that we discussed. All right. I think everybody kind of have something like this, right? So let's identify different component and you tell me. So what's the desired speed, the first one here? The input. So I know you had system and signals and system and you know all of this. You want to make sure everybody is on the same level once we get to next week. What's your amplifier? Which component is the amplifier? What? Controller. You can amplify a signal. The DC motor, what's the DC motor? Actuator. What's the rotating disc? I teach you. The process. And what's the actual speed? Javed. Oh, sorry, Shujin. What's the actual speed? Huh? I know, like from the components of an open loop system, which one would be that last one? Jeffrey. Output. right? So we can call these two together plant, but that's just vegetable. Good. Now that we know how does the block diagram look like, and you're able to draw the block diagram of a system by looking at the component of it, right? Now I want you to know how to calculate the error of our open loop. So now what would be the source of the error? So if we have a runtime, and let's say the timer goes, the controller does its job, and then there's actuator, there's a process, so everything has to be good. And then I said, I don't need to check my output, right? So I'm trusting this process is going to work. So why do we need to find the error? Where is the source of the error? Where could be the source of the error? What could go wrong in our process and we don't get what we wanted? Kevin? That's an untuned controller, so that's one thing. Let's say we tuned our controller. The controller is pitch perfect. The timer works like a clock.
Respond to external interference with the output, like
yeah, so something from environment. You remember from last class we said environment because every system is in an environment, right? So it could have noise from the environment. Now, do you remember that we called what like the process? So we could have process noise. The disturbance that comes from the environment and applies to our system, we'll call that process noise. So let's say you're driving a car, you're going 25 miles per hour, perfect, and then you hit a bump. Would the speed of the car change or not if you don't push the pedal more? It would slow you down, right? Because instead of going straight, you went a little bit high, so there will be like some loss in your system. So that's your process noise. So now even an open loop system can have process noise, right? So we want to know how to calculate that error that comes from the environment. So the error would be, I'm going to put OL, open loop, input minus output. So now the input is always a reference. So when we say input, it's our reference input that we had our desired value is different from input to the controller. So let's look at this system. We have R, which is the first, it's our input, but this is our reference input. Then we have our controller. Then we have U, which is the input to our plant, right? That's the thing that controls the actuator. So if you had a desired speed, that's actually your reference input, is not what goes to your DC motor to move the thing for you. So you have reference input, controller, your plant that has input to it, and output. So this YOL is Y of the output of your open loop. Now the error is, look at the reference input that you want it to be 25 miles per hour. Now look at the output, how much you got. Is there a difference? Okay, we're not controlling, like we're not manipulating our controller. We just want to know if there is a difference. We need to know that. So then you decide, do I need to design something extra? Or this works fine, I'm good. So to do that, there are different ways. I found it easy. If you find the value of U to your plant, and then find the value of your Y output, YOL, and then compare YOL with your R. So you kind of know what's the input to your plant. So let's say, what is your U? This is signal and system. So you have R going in 1/10. So let's set the controller gain to 1/10. So it's already set for you. So R is going into this and U is coming out. So U is 1/10 of an R of whatever reference we had, right? So our controller is descaling our input, whatever it is, like 1/10. Now from the plant, YOL will be this U that went in, go to a summation point, there is this process noise, W, times 0.5, so here this signal is 0.5 W, minus U coming in, so this is U minus 0.5 W, going into a block that is 10, so 10 times of that is YOL, right? So now I'm gonna write down YOL is 10 times U minus 0.5 W. Okay, I don't understand. I'm gonna turn this off. I think I'm loud enough. If you couldn't hear me, just let me know, I yell more. Because this is creating a lot of noise, which is the environment noise, right? So 10 times U minus 0.5 W. I have U from the previous stage, right? Is 1/10R, R/10. So I can say 10 times R/10 minus 0.5 W. So this is R minus 5 W. Correct? So I have this one. Now the error would be input R minus 5 W is R minus R plus 5 W. So these two cancel out. So E open loop is 5 W. What does that mean? Well, it means that this current system, there always would be a small error if I had any noise from the environment, right? Let's say this was a car, your reference input is 65 miles per hour. And then your noise, let's say was 1, which is like, let's say 1% error due to the road or construction. We want to know with this system, which we already developed what the error looks like, what is our YOL? What would be the actual speed? How can we calculate that? What would be the actual speed? What?
Whatever 95%.
Yes. Which is, so that I was like, what do you mean? But I get it. So 5, so error of, you actually calculate percentage error. Error of open loop for this system is 5 times W, 5 times 1, which is 5, which is equal to input minus output. So 5 is equal to 65 minus actual speed. So actual speed is going to be 60 miles per hour, which is 95% of the actual. So this is good, give you an idea. If your system, so you can, if you're designing a controller, you want to decide if it should be open loop or closed loop, you can check it for a couple of scenarios that can happen and check your error, get the percentage. If it's like below 1% and you're happy with below 1%, you don't design anything after. Open loop is good enough for you. But what if it wasn't good? You could get more error out of this. Instead of 60, you would give 35, is not good. Or so you wanted to manipulate your output. What would you do that? How would you do that? Sorry. I'm sure most of you know. We get a feedback from our output and look at it, which means makes it a closed loop, right? So the drawback is we cannot change the output based on the variation of this in the system, which basically is the noise. And the solution is to close the system, meaning that get a signal from the output signal, send it to our input, which is our reference input, our desired value, compare them, look at the error. Is the error acceptable? No, send that error to our controller. It will manipulate it, give us a variable that we can control the actuator. So it's meaningful for the actuator. Because the difference would be 65 miles minus 60 miles, 5 miles. Go to a controller, 5 miles for a DC motor doesn't mean anything. The controller does its magic and gives some voltage. Hey, you need to pump up this much or rev more. Then it becomes, so it is always a meaningful variable for your actuator, and the two sides are different. So the units are always, most of the time, different from going into the controller and coming out of the controller. How it looks like, we had our, so pretty simple if you want to say compare to your open loop. You have controller, actuator, process, that was your open loop. Get a signal from your output. You can put a sensor, or you can say, no, like I have a perfect sensor, and you can just put a line like that. This means that my sensor gets 100%, there's no error from the sensor, and I get all of that, and I can compare. When you have sensor, there is a drawback on how, like, you have to use sensors, but the thing is, depending on the quality of the sensor, there might be some error. That's the noise from measurement. That's the second noise we introduced to our system, which you will learn how to deal with that. So if you had a sensor, you will have some sort of noise, but sometimes in our practice to learn things, we're gonna put a simple line. That's still a feedback. It just means 100% of everything went. So we have the perfect sensor, all right? So you get that sense variable, commanded variable, you compare error feed to the controller, right? So what I want you to do before doing this, I want you to draw a closed loop system for one of the example we've done, or you can choose car cruise control. But I don't want you to look up online. I want you to think about the system, draw it. Draw that and submit on Carmen. I think that would be the end of the class because we don't have time for the rest. I'll pick up on Wednesday. But submit this before you leave. I will post an annotated version which has the solution to this guy, but I'll talk about it in class. So if you have a question about the quiz, PP1, I post the solution, you will see, but most of you got the question that was about homogeneity, superposition, and time invariance wrong. The quiz had time invariance. The alpha is time invariance. That's why I lost time. That's the question. I'll print the quiz and answers, so you can see the question. You have to submit your solution, so don't forget. Recording. That's the end of today's recording.